So let's continue. We're gonna start chapter 14, introduce it to some extent, and then we'll get back to the other chapters as we finish the course later. So we talk about synthetic polymers. Synthetic meaning man-made. Okay, you can make these polymers in the lab. You see, you have nylon 66 over there. You have nylon 6 there, and yeah, and you can see the application. That's a polymer right there used to make this intertwined rope. Polymers are used to make containers like where you carry your milk, containers for carrying your drugs, the discs, covers. You look around, all you see is polymers. You see polymeric flasks, and so on and so on. Threads, yarns used to make clothes. Your DNA is a polymer, RNA is a polymer. Trees have a polymer called cellulose that's found in the wood. Starch is a polymer. Silk, a natural polymer. Styrofoam. You know styrofoam? The packaging material that's used to make peanuts. That's a polymer from styrene. Okay, so poly means many. Ma is just a compound. So many small compounds joined will give you one polymer. Those small compounds that are joined are called monomers. Mono meaning one. So single basic units joined together will give you a polymer. Those single basic units are called monomers. Alright, so polymers are large molecules. They fall under the class called macromolecules. Macro meaning big or large. They are produced by joining or condensation of small units called mono meaning one monomers into a long chain which we call a polymer. Monomers can be the same or they can be different. When they are the same, the type of polymer you get is called homopolymer. When the monomers are different, you get what we call heteropolymer. Okay, so one single polymer made by joining two different structured monomers is called hetero. If the monomer has the same structure, for example, if you join styrene, you're gonna make styrofoam. This is how we represent polymers. You make styrofoam where this unit is inside the structure and repeated so many times, n times, a million times, you get a homopolymer because it's made of only one monomer, what happened to be the styrene. Alright, so you have naturally occurring polymers, which could be proteins, carbohydrates, which is polysaccharides, RNA, deoxyribonucleic acid, and ribonucleic acid. You learn those in biochemistry. Those are examples of polymers, and the single units that make the RNA and DNA composed of amino acids are joined to a sugar and a nucleotide. You learn that in biochemistry. So let's classify polymers. Polymers can be classified in so many ways. So you can classify them based on how they are formed. You can classify them based on structural composition, which that's how I named it as homopolymer or heteropolymer. But let's talk about classification according to the way they are synthesized, the way they are made, the way they are synthesized to make synthetic polymers. So the first class is chain growth or addition polymerization. Very simple to understand. You're growing the chain or you're adding monomers to themselves. You get a polymer, you retain all the atoms of the monomers, no loss of small molecule. And those who are taking 263 lab, you're probably gonna finish the class with this polymer lab. So no loss of small molecule like water, HCl, nitrogen gas, you don't lose those. All atoms stay as you click the monomers together. But in condensation, it's characterized by the loss of small molecules, and that leads to fewer atoms in the polymer. Okay, fewer atoms in the polymer, and the loss of the small molecule could be water, it could be HCl, it could be nitrogen. Those are the most common small molecules lost during condensation or step growth polymers. Now these step growth polymers can be used to make nylon or ester polymers. It's condensation, so we lose small molecules. Okay, so the atoms will be fewer in the polymer. In the chain growth, all atoms stay. So another characteristic of chain growth is that it's gonna go through formation of radical cations or anions. But before we talk about that, let's look at examples of chain growth polymers. So first we're going to consider monomers that make the polymers, and then the uses are listed in the table. I won't go through all of them. So whenever you use ethene as a monomer, you're gonna get polyethylene. Common man will just call this polyethylene, which is the plastics that are used to make molded bottles, toys, okay, some cable covering, and shipping containers. Okay, so the basic component CH2, remember it's chain growth, so no loss. So this is how you do it. I know the mechanism is coming. So if you're starting with an alkene, and you see most of these have alkenes, that's one characteristic of this chain growth. That's another characteristic of chain growth. So usually you want a radical initiator, so which will help this pi bond to break apart by what we call homolytic cleavage. Okay, you are breaking the bond, moving electrons aside. So you will end up with let me show you what you end up with. So in fact, this R will come and join with this single electron. So on one side you end up with the radical, on the other side the CH2 on the right uses the single electron to join to the radical initiator that starts the process. We talked about radical mechanism, so you should be remembering that. So you see, this can be a new radical, play the role, this molecule, this radical intermediate can play the role of this R dot to react with another monomer. So I'll need to use a different color. So let's say you have CH2, the second monomer coming in. So this CH2 will now bond with that CH2. I'm moving single electrons with fishhook. The other electron goes on the other side. So you're gonna end up with CH2 radical. So this is the propagation step. The first step was initiation. Now this is propagation. So you get the CH2, this CH2 right here is now joined to the blue CH2 to the left. It's this CH2. and then you have the other CH2, and you have the R. Notice that you're making a new radical, right? So this is propagation. So propagation will continue so many times until the last monomer reacts. You keep growing the chain. The basic unit that's repeated is this part, right? So to show the polymer, we usually just draw this hanging bond, okay, and the other hanging bond, and then use parentheses, and then say this unit is gonna be repeated in the polymer, let's say n times. Okay, so n is number of times the monomer is repeated in the polymer. In other words, n represents how many monomers were used to make the polymer. So this is a polymer called polyethylene because it came from ethane. Alright, so I've given you an overview. So all these double bonds will do the same thing. All these double bonds will do the same mechanism. Okay, so if you're using propene, you get poly, many propenes. If you use styrene, you get polystyrene, otherwise called styrofoam, used for packaging, making plates, disposable food containers, disposable cups. Then you have acetonitrile, which makes polyacrylonitrile, used for sweaters and other clothing for those who like swimming and sports. The stretchy fabric might have been made using polyacrylonitrile or acryphene. Oron. Vinyl acetate makes polyvinyl acetate, which is used to make glue or adhesives. And then methyl methacrylate, which is this structure, the whole thing, is used to make polymethyl methacrylate. That's used to make periglass. What you have on your phone screen, this glass must be made from periglass. The covers that you use to protect the screen of your phone, most of them are made from periglass. Okay, and then you have vinyl chloride. Vinyl chloride make PVC. Of course, those are pipes that you use for drainage and in toilets. Okay, or pit latrines, if you know what those are. Tetrafluoroethylene. They're used to make polytetrafluoroethylene, which is Teflon. You know, Teflon is used in plumbing to seal pipes so there's no leakage, or it's also used to coat utensils and as insulators. So you have an idea of the mechanism of chain group polymerization. As I showed you, we are growing the chain. You see, you create the first radical by initiation and then make a new radical by propagation. Okay, and then you at some point when you attack the last monomer, you do termination, you get your polymer. Okay, so there are three basic mechanisms in producing chain group polymers. One is free radical mechanism, which is what I've described here, and it's gonna come back. The other one is cationic chain growth. Here you have to go through formation of carbocation intermediate. Carbocation intermediate. Here you have to go through formation of carbanion intermediate. Now, for those who've forgotten, carbocation is where you have a positive charge on a carbon. Okay. Carbanion is where you have a negative charge on a carbon. Okay, so negative charge, carbanion. Positive charge, carbocation. Okay, so those are the if a mechanism involves radicals, cations, or anions, most likely you are going through chain growth polymerization. All right, and like I described for CH2 that went through forming a radical using a radical initiator. Okay, you formed a radical by initiation, and then the radical propagated. Okay, let's see. I'm just giving you the overview to repeat myself here. So the radical propagated once you brought a second molecule of the ethene, you get a radical. You conserve your atoms, CH2, CH2, they're still CH2, CH2, and then now that piece was joined in our mechanism to the red piece. If you keep doing that, we ended up with CH2, CH2 in brackets with an N outside. What that was polyethylene. So do you do the same thing with this guy? Since the atoms are conserved, what you need to do as a shortcut, just assume this will break, the one electron go to that side, the other electron go to that side. Okay, so remember what we said with chain growth, the atom counts are conserved, so I know I'm losing the pi bond, but this structure should be present. So as the electron moves to this carbon, that electron can be used to make a bond going to the right, and that as this electron goes to CH2, that electron can bond to another electron to make a bond to the left. Okay, so and this monomer can be repeated so many times to grow the chain, so chain growth polymerization. So we'll put N here to represent again number of times monomer is repeated in the polymer structure. You have to put the N there. So you see, this is a vinyl, this is called vinyl chloride. So if many vinyl chlorides are conjoined, you get polyvinyl chloride, PVC, which is used to make pipes and so on. So as you do, after the initiation, you do the propagation. So propagation propagates, adds more of the monomers. So you get, like here, what is shown here is that you have a polymer that's joined by adding several replicates of its monomer. So you're growing the chain, so it's chain growth of the vinyl polymer. Usually we don't need to show these guys. We just know that this bond must be bonded to another monomer, that must be bonded to another monomer, and that's what I do right there. Okay? You only show the repeated unit of the polymer. Okay, so like all free radical reactions, there is an initiator required. You see how I'm saying here R dot, and here I said R dot. You need something to start the process. So the R that I've been using to start the process to initiate, for initiation step in chain growth mechanism, is benzoyl peroxide. So whenever you have benzoyl peroxide, you can see the molecule is bulky, the oxygen oxygen bond, this bond right here is weak. So it's most likely gonna cleave. You know, a bond is made by 2 electrons. So each of those electrons taken aside So you're gonna get two equivalents of the same molecule with the radical there. Now here you do have two lone pairs of electrons, but after you give these oxygens an extra electron, okay, so you're gonna get 5 of them. So this guy is unpaired. Because it's unpaired electron, it's not a lone pair, so we call single unpaired electrons radicals. Okay, so you get two radicals because you're cleaving and cutting the molecule into two halves. You get two equivalents of the radical. We call it a benzoyloxy radical. Now the benzoyloxy radical can lose CO2, and this is how that would happen. This is just for your information. I won't test you on this. So you can donate probably the extra electron out of the 5 to make a double bond, and then use another here. Use another electron from this bond. Okay, so you're bringing two electrons together, you're making a double bond. So in which case, this is what you would have, right? This would be the extra electron, but that's the wrong shape because CO2 must be linear. And then the other electron is donated to the carbon of the benzene ring. So these two electrons are coming together to make a new pi bond. Okay, and the other electron left will be given to benzene. So that gives you a radical. Okay, we get phenyl radical. So you have two types of radicals when benzoyl peroxide is used. Is heated. So you either get the benzoyloxy radical and the phenyl radical. Okay. So this peroxide is important to make the radicals, and those radicals are then used to initiate the process. So for example, if you're using the vinyl chloride that we just looked at, I showed you the shortcut on how to get PVC. It just says radical initiator, and that's what you're talking about. So if this thing is split apart, you might end up finally getting phenyl radical. You can use the phenyl radical as an initiator to react with the very first monomer, okay, to make the very first radical. And that's the process of initiation. You're making the very first you're making the very first radical out of your monomer. Initiation step. So your phenyl radical, which is the R dot radical initiator, will open up the pi bond of the vinyl group, because I told you chain growth most likely work with vinyl containing compounds. A vinyl is just a CH2. A vinyl is just a double bond between two carbons. Okay, that's a vinyl. Represents an alkene or substituted alkene. So going back here, the pi bond donates its one electron to join with the other electron in your radical initiator. You're making a bond between this CH2 and the benzene ring. So this is the CH2. Now a new bond is now created when these fish hook arrows bring one electron each. You get two electrons, which make this bond right here. Okay, so here you do have a hydrogen, is still there, but you opened up the pi bond to the right, giving the electron to the carbon, which gives you this radical. This is the first carbon radical that will be used in the second step of propagation. Okay, so since you made your first radical, it's gonna be used to make new radical. It's gonna be used to make more radicals or new radicals. So that step is propagation. To propagate is to make more. Okay, so This radical is made from initiation step, so you use the electron to join with another electron from the pi bond of a second monomer, and the second electron of the pi bond will be donated to the carbon next door. So two electrons are meeting here, two electrons are meeting right here, and they will be used to make a bond. That bond is this bond now. Okay, so you see you have a CH2 here, which will be this CH2, and then the second electron was given on the other side, gives you a new, that's a new radical formed, and that's characteristic of propagation. You make new radicals. Meanwhile, you're growing your chain. Okay, this is the first monomer you created from your radical initiator. From this step, you made this radical by joining to the first monomer. This is the second monomer. Okay, so that's the first monomer, that's the second monomer, and this process can keep going so many times until you add the nth monomer. The nth monomer could be the millionth monomer, could be the 10 billionth monomer. So the process will continue several hundred thousand steps depending on 1. Temperature, 2. Pressure, 3. Solvent, 4. Catalyst, and so many other factors beyond your scope. So you grow the chain by propagation. So the growth actually happens in propagation. Now, if you've made so many long fragments, so let's say one fragment, let's say this guy has 100,000 monomers, and probably this one has 10,000 monomers. These two monomers can decide to stop the process by what we call termination. To terminate is to stop. This can occur by one or two mechanisms. One is radical coupling, so where two radicals of the polymers, they are still long chains, they are fragments of the polymers, close the reaction by the two electrons joining using fishhook arrow. Remember we said fishhook arrow is one electron movement. I'm assuming you know that. So if these two come together, two electrons are coming together, you're making a new bond. That's a new bond because a bond is two electrons. Notice that no radicals. There's no more radicals, and that's characteristic of termination. It's closed, it's finished, finito. So to represent this polymer, instead of drawing the 110,000 monomers in the structure, we just usually spot the repeated unit. I see this is repeated, this is repeated, this is repeated, that's repeated. So to show the repeated unit, I'll just show a hanging bond and a hanging bond, and my n, number of times the monomer is repeated. Remember, we started with a CH2, CHCl, right? Our monomer was CH2, the vinyl chloride, CHCl. So all those elements are represented in there. Okay, we've not lost any hydrogen, we've not lost any hydrogens, we've not lost any carbon or chloride. So that will be the polyvinyl chloride, PVC, which is made by radical mechanism, initiation, propagation, termination. No loss of any molecule. So that's one way of termination. What is the other method of termination where there will be no more radicals at the end? Okay. So the other method of termination is radical disproportionation. This is where the terminal carbon reacts with a hydrogen atom adjacent to the carbon radical of another chain. So this hydrogen here, okay, that hydrogen is called the beta hydrogen, can be taken out by a second molecule. So let's assume again in this polymer, you see this is a weakly line, meaning that this is a polymer. let's say that this has 1,000 monomers, okay, and let's say again this has 10,000 monomers, so it's still a polymer because a big molecule with 10,000 repeated units in it. So these two are polymeric radicals, but instead of clicking these two electrons together to make a bond like we did on here, we are going to do beta elimination. So this one looks like some type of E2 reaction, actually not E2, I think E1 reaction. In fact, we would call it false, meaning pseudo, okay. We'll call it a false E1 mechanism because we don't have a carbocation, so it's false, but it looks like an E1 because you're ending up with a diamond. So these 100,000 monomeric, this 100,000 polymeric compound containing 100,000 monomers can be used to take out this hydrogen, okay? So use this fragment, let me just simply say, use this radical fragment to deprotonate the beta hydrogen of the other radical fragment. So use this electron to make a bond with an electron from the hydrogen bond, and then the other electron is donated in between these two carbons, which is generous enough to donate its own radical electron. So you're making a double bond right here. At the same time, you're clicking your hydrogen on this carbon. So that's the hydrogen that came in. You do have a hydrogen here, but now you've added an extra hydrogen. So you have two hydrogens. Again, no more radical. But in between here, you're making a pi bond, which is this pi bond. Again, this is not a radical, no more radical. That's the characteristic of termination. There's no more radical to your right side. And this process is radical disproportionation. So you're breaking something from another molecule, you're disproportionating it. It produces unsaturated alkene and an alkane. We usually don't want this to happen because you ending up with neutral fragments, neutral polymeric fragments, which are mixtures compared to what you really wanted. Okay, the other way, oh, I think we're done with termination. So there could be side reactions, unwanted side reactions that could happen. Okay, it's still some form of termination, but in this case you're gonna have a radical happening, a radical being released. We usually don't want this to happen, okay, but it might. Okay, so this time assume that your 100,000 mono, your 100,000 polymer, your polymer containing 100,000 monomers probably is reacting with another polymer of itself or one that has fewer monomers, let's say 10,000 monomers in this polymer. So this radical can be used to take out, this time is taking out an alpha hydrogen. You're not taking out a beta hydrogen which is on the carbon next door, you're taking the hydrogen bound to the carbon bonded to the chlorine. So use an electron, a bond is two electrons, use an electron to bind to the carbon radical, so which means this hydrogen is taken out. You do have a hydrogen here, now you're gonna end up with two hydrogens. So this is neutral. After this carbon removed the alpha hydrogen or accepted the alpha hydrogen, that's neutral. Now the other electron to this hydrogen will be donated to the carbon. So you're making a new radical. You see how that's useless? So this type of termination is not good. It's termination, yes, because you are closing this radical. Maybe this would be a polymer already, so it's terminated as a polymer, but it's a shorter polymer, which we don't want. Okay? So this creates a problem because now you might end up with branching. The chain propagation would now continues from the carbon radical in the middle of the chain, resulting to a branched polymer. So you see that this is neutral. You made a new radical, which happens to be branched because you see you have the R groups and then you have the chlorine. So we usually don't like this type of termination that gives us a neutral polymer because it gives us new radicals. So to prevent this type of messy radicals being formed, for example, from this step, we use radical quenching reagents. So this is what we usually call radical scavenger, which is usually used to stop the polymerization process, which might be going with unwanted products. So you use thiols, they are smelly, they smell so bad. And that's the characteristic smell that you get from a skunk. They are thiols. Okay. So you can add a reagent after your reaction and after you're satisfied that your polymerization is done. Okay. So you add radical scavenger. The sulfur radical is very stable and usually don't react after. That's why we use sulfur reagents. So to show you the process, okay, so the radical from the carbon will join with an electron from the HS bond. So you're making a new bond between the hydrogen and the carbon. Okay, you had a hydrogen here, so now you have two hydrogens. You see now this guy is neutral, no more radical on that one. But now the other electron will be donated to the sulfur, and that's how you make the sulfur radical, which is by far very stable compared to you having a radical on a carbon. And now this sulfur radical tend to join to another sulfur radical. So these two guys can cojoin by homogenic bond formation, like you're bringing the two electrons together, you make a new bond. So overall, no more radicals. So when your reaction is done and you really want to make sure you don't want any radicals in your flask, just add the alkyl thiol group, and the thiol will help you to kill any radicals in the system, and even itself will close up itself to make the disulfide bond, which of course your enzymes in your body likes to have. All right, so we'll continue from here. Physical properties of polymers.